Method of induction is the name of the topic that we are going to take today. Method of induction. Now, what are we going to learn in this topic? In this topic, method of induction, we are going to prove, we will prove certain propositions. As you know, in mathematics, we have propositions. So we will prove certain propositions. These propositions will involve natural numbers. So what are we going to do? We are going to prove certain propositions involving natural numbers. Natural numbers. When I say propositions involving natural numbers, what does that actually mean? When I say propositions involving natural numbers, what does that mean? I give you an example for this. Now, as you all know, if I have 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus so on up to n, so this is equal to n into n plus 1 upon 2. So by proposition, we mean such a thing. See, this is, here we have a left hand side, we have a right hand side, and these two are equal. So in this, what are we stating? What is the statement? What is the proposition? A proposition is a mathematical statement. What are we saying here? We are saying that the sum of first n natural numbers, the sum of first n natural numbers can be given by n into n plus 1 upon 2. That is, if you are adding first 50 natural numbers, if you are adding first 50 natural numbers, you can directly use the formula. N value is 50, so you can write 50 multiplied with 50 plus 1 divided by 2. So this is 25, then 25 into 51, whatever you get. 25 into 51 is your answer. So such propositions we can prove using mathematical induction. This was one. Like I can give you, similarly, I can also give you, suppose, so as you had 1, see, similarly, you can have 1 square plus 2 square plus 3 square plus 4 square plus 5 square and so on plus n square. What is this? This is sum of a square of first n natural numbers. Sum of squares of first n natural numbers. And it is given by n into n plus 1 into 2n plus 1 upon 6. Okay. So if you have, see, these all are propositions. This is a proposition. What are you stating in this proposition? You state that the sum of squares of first n natural number is equal to n into n plus 1 into 2n plus 1 upon 6. For example, it means if I have sum of square of, say, first 20 numbers, if I have sum of square of first 20 numbers, I want to get the sum. So instead of writing the actual square and adding, we can just write n as, see here, n square. What is n here? N square. N here is 20. So you can have 20 multiplied to 21, n plus 1, 21. This is 2n plus 1. So this is 41 divided by 6. So then whatever 3 sevens are, 3 twos are, 2 tens are. Okay, 3 sevens are 21, 3 twos are 6, and then 2 tens are 20. Okay, so 7 ones are 7, 7 fours are 28, and then this, see. So 2870 is the answer. If you add the squares of first 20 numbers, you will get 2870. You'll get 2870. So like this, we have plenty of propositions which we can prove. Now see, these propositions, what are they involving? They involve natural numbers. Here n is a natural number. You see this? So such propositions can be proved with the help of method of induction. We can prove these propositions with the help of method of induction. So that you need to first follow. Now proving a proposition is the proving a proposition using mathematical induction requires expertise. It requires expertise. Okay, why? Because if you want to do that, if you want to prove the propositions using method of induction, you will have to know the principle of mathematical induction. You will have to learn principle of mathematical induction. So what are we going to do now? We will learn the principle of mathematical induction. Let us study this principle of mathematical induction. So I will write the principle of mathematical induction. It goes as follows. I want your attention. Okay? You all need to be very attentive. See here. It goes as follows. When a mathematical proposition is true for n equals to 1. Okay. Now here, since we are using n equals to 1, you know, I must write the proposition as P of n. Okay, so a mathematical proposition. Now, you already know what is a mathematical proposition. So when a mathematical proposition, I've already told you, a mathematical proposition is kind of statement which will have left hand side and it will also have right hand side. Okay. So when a mathematical proposition P of n is true for n equals to 1 and and if P of n is true, if P of n is true for n equals to k, then it is true for n equals to k plus 1. Then it is true for n equals to k plus 1. In such case, we can say that P of n is true for all n natural. See, in beginning, the principle of mathematical induction appears to be a bit tricky, and for beginners It might seem difficult, but that is not the case. I'll tell you the way you have to learn it and understand it. See, remember that in principle of mathematical induction, there are actually two stages. There are two stages. The first stage is you will prove that the proposition is true for n equals to 1. In the first stage, what you will do? You will prove that proposition is true for n equals to 1. You will prove that proposition is true for n equals to 1. See, this is the first stage. What is the first stage? First stage of mathematical principle of mathematical induction. The first stage is you will prove that it is true for given proposition P of n is true for n equals to 1. You will prove that it is true for n equals to 1. Now comes the second stage. You have to understand the second stage. See, the first stage, and you check the word and. Now you have the second stage. See, the second stage is if P of n is true for n equals to k, then P of n is true for n equals to k plus 1. This is second stage. In the second stage, what you are going to prove? In the second stage, you will prove if P of n is true for n equals to k, you will prove if P of n is true for n equals to k. You will prove if P of n is true for n equals to k, where k is some integer. Then P of n is true for n equals to k plus 1. So as such, in second stage, you have a assumption first. What you have? You have an assumption. What is the assumption? The assumption is P of n is true for n equals to k. See, the second stage, how does it follow? It starts with if P of n is true for n equals to k. It means you will have to assume that P of n is true for n equals to k. Under this assumption, you will prove it is true for n equals to k plus 1. It is true for n equals to k plus 1. And when you have proved these two stages of principle of mathematical induction, you can apply the method of induction and you will know that you got the final thing done. That is the whole, then you can say that the given proposition is true for all n which belongs to set of natural numbers. So I give you an example here. See what will happen. Suppose you have P of n. Okay, there is one proposition you have which you write it as P of n. So what is the first step? The first stage is you prove that P of n is true for n equals to 1. Okay, so proved. Okay, I'm writing proved because yes, any problem I start, I will prove it. So suppose I proved that P of n is true, P of n is true for n equals to 1. Okay, P of n is true for n equals to 1. This is my first stage. Now I'll move to the second stage. See, what is the second stage? The second stage, I prove, okay, prove what? If P of n is true, if P of n is true, if P of n is true for n equals to k, then it is true it what does that it mean? It means P of n. Then P of n is true for n equals to k plus 1. I will prove this part. What is this part? If P of n is true for n equals to k, I will prove if P of n is true for n equals to k, then P of n is true for n equals to k plus 1. And once I have done these two steps, this is first step and second step. Once I have proved these two stages, I can apply the method of induction. How? See, the second stage which I proved, it says if P of n is true for n equals to k, then P of n is true for n equals to k plus 1. So it means if P of n is true for n equals to 1, here in place of k now you write 1. So if P of n is true for n equals to 1, then P of n is true for n equals to 1 plus 1, 1 plus 1, because you have proved for n equals to 1. You have proved it for n equals to 1. I hope you're getting it. I have proved it for n equals to 1. So when I have proved it for n equals to 1, it is true for n equals to k plus 1, that is 1 plus 1. And if I have 1 plus 1, it is true for n equals to 2. Okay, so P of n is true for n equals to 2. So it means P of n is true for n equals to 2. So now I have P of n true for n equals to 1, which I have already proved. And I also have P of n is true for n equals to 2. Then next what I will do is I will put n as, so if now again apply second stage. In the second stage now I will say P of n is true for n equals to 2, then P of n is true for n equals to 2 plus 1. So it is true for n equals to 3. See, now it is going in succession. You are applying the method of induction in succession. Now you say P of n is true for n equals to 2, then P of n is true for 2 plus 1. P of n is true for n equals to 2 plus 1. That is, it is true for n equals to 3. So P of n, you proved that it is true for n equals to 3. Once again you apply. If P of n is true for n equals to 3, if P of n is true for n equals to 3, then it is true for 3 plus 1. That is, P of n is true for n equals to 4. Again you apply. So if P of n is true for n equals to 4, then it is true for n equals to 4 plus 1. So you proved it is true for 5. Once again, now you prove it for n equals to, now you can say that since P of n is true for n equals to 5, so it is true for n equals to 5 plus 1, that is 6. And now you can understand, this way you can prove for all natural numbers, and you have proved it. So I repeat again, the principle of mathematical induction goes in two stages. What is the first stage? The first stage, you will prove that P of n is true for n equals to 1. N equals to 1. You will prove it is true. P of n is true for n equals to 1. Then what you will do? You will prove that if P of n is true for, you will prove if P of n is true for n equals to k, then P of n is true for n equals to k plus 1. So if it is true for n equals to k, then it is true for n equals to k plus 1. And then since you will have proved both, you apply the method of succession. That is, n equals to 1, you have already proved, but you know if it is true for n equals to 1, it is true for n equals to 1 plus 1, that is 2. Then here 2, so this will become 3. Then here 3, so it will become 4. When here 4, so it is true for 5, and so on. The things continues. Let's start with the problems on principle of mathematical induction. So here in exercise 4.1, that is from Maharashtra State Board textbook for 11th standard. The question goes as prove by method of induction. Prove by method of induction for all n naturals. Okay, so the first question I take, see, we have to prove that. To prove that 2 plus 4 plus 6 plus 8 plus dot 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 plus 2n equals to n into n plus 1. Okay, n into n plus 1. This is what I have to prove. N into n plus 1. So in short, what I have to prove? I have to prove that sum of first n even numbers. I have to prove that sum of n even numbers, first n even numbers is equal to n into n plus 1, n into n plus 1. Okay, so it means 2, 4 plus 6 plus 8 plus dot 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 dot, and suppose here I have 2 into 20. Now what does that mean? See, this is 2 into 1. Try understanding. This is 2 into 1. This is 2 into 2. 6 is 2 into 3. 6 is 2 into 4 is 2 into 2. 6 is 2 into 3. You see this? So 8 is 2 into 4. Like this. Here I have 2 into 20. So what is this? This is sum of first 20 numbers. Sum of first 20 even numbers. First 20 even numbers. As such, this is 40. 2 into 20 is 40. So as such, if you are adding the 2, 4, 6, 8, so on till 40, what are you going to get? You are going to get, just apply the formula. Where you have n, you write 20. So 20 into 20 plus 1, that is 21. 20 into 21. So 20 into 21, that is equal to 421. How much is this? 420. How much is that? 420. Okay. So that's okay. Let us now prove it. See, I have to prove. What I have to prove? This proposition. So see, the first thing I do is I assume this to be P of n. So see, how do I write it? I will write let P of n, okay, let P of n be this. That is 2 plus 4 plus 6 plus 8 plus dot 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 plus 2n equals to n into n plus 1. This is P of n. Okay. As you know, the principle of mathematical induction goes in 2 stages. What is the first stage? The first stage is I will prove that this P of n is true for n equals to 1. So see, here I write, we will prove that P of n is true for n equals to 1. This is my step 1. Okay, this is my step 1. What is the step 1? Step 1 is we will prove that P of n is true for n equals to 1. Okay, so how do you prove? Very simple. In left hand side, you put n equals to 1. See, this is the proposition. This is the proposition that you want to prove for n equals to 1. So how do you prove it? you will take n equals to 1 in the left hand side. Okay, so see, so I want to prove p of n is true for n equals to 1. That is to prove that is to prove that n equals to 1. Okay, that is to prove that p of 1, see, n is 1. So what will this become? It will become p of 1. That is to prove that p of 1 which is, see, now when you write n as 1, try understanding. N is the term. What is n? N is the term. N is the term. So when n is 1, you have just one term. And what is just one term on the left hand side? 2. That is to prove that p of 1, which is 2, equals to, now here you write n as 1. 1 into 1 plus 1. That is to prove that this is true. This is true. See, in order you prove p of n is true for n equals to 1. Now here you have the proposition. What best could it be than proving this? If you want to prove p of n is true for n equals to 1, it means you have to prove that this thing is true for n equals to 1. That is p of 1, which is 2 equals to 1 into 1 plus 1 is true. That is to prove that p of 1, which is 2 equals to, see, 1 plus 1 is 2, 2 into 1 is 2, true, 2 equals to 2 is true. Okay, now 2 equals to, you have to prove that 2 equals to 2 is true. So here what you will write, which is obviously true, okay, which is obviously true. Therefore what you will say, you will say that p of n is true for, n equals to 1. So you have proved that p of n is true for n equals to 1. The first stage is over. See, it is time now we'll go to the step 2. What we have proved in step 1, we proved that this proposition is true for n equals to 1, that is when there is just one term. So when there is just one term, so this proposition holds true. Now we have step 2. Step 2 is, as you know, in step 2 we have an assumption. See, what we have to do in step 2, we will prove that if p of n is true, for n equals to k, then p of n is true for n equals to k plus 1. See, this is step 2. Now in this step, what we are going to prove, we have an assumption that is to be followed. Students, many of you do not pay attention to this thing. What you have to prove that if p of n is true for n equals to k, then it is true for n equals to k plus 1. It means this part is your assumption. you will, under the assumption that P of n is true for n equals to k, you will go ahead. You will first assume that it is true for n equals to k. You will prove, you will assume that P of n is true. You will assume, I repeat again and again, I repeat, you will assume that P of n is true for n equals to k. And under this assumption, you will prove that P of n is true for n equals to k plus 1. Okay, and once you are done with it, what you will then say, you will use the method of induction. You will say replace k by 1, so it will become, if P of n is true for n equals to 1, then P of n is true for n equals to 1 plus 1. That is, it will become true for 2. It will become true for 2. Then you will replace, since you have proved it for 2, you will replace k by 2. You will say, since P of n is true for n equals to 2, P of n has to be true for n equals to 2 plus 1. That is, it will become true for 3. And once it is true for 3, you will write P of n is true for 3, then it is true for 3 plus 1. That is, it will become true for 4, then 5, then 6, then 7. And this way it is true for all natural numbers. So here we have to first make an assumption. What is the assumption? We will make an assumption that P of n is true for n equals to k. So I'll write here, let P of n be true. Let P of n be true for n equals to k. That is P of k. See, here you will write n as k. So P of k, which is 1 plus, which is 2 plus 4 plus 6 plus 8 plus dot 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 plus 2k is equal to k into k plus 1, okay, is true. See, we assume that this thing is true. It is true. Now, under the assumption, I will prove that P of n is true for n equals to k plus 1. I assumed it is true for n equals to k. Now using this, I will prove that it is true for n equals to k plus 1. See how I do it. I will write this as 1. I write using 1, we will prove that P of n is true. P of n is true for n equals to k plus 1. That is to prove that what you will do in this P of n, you will replace n by k plus 1. That is to prove that P of k plus 1, which is 2 plus 4 plus 6 plus 8 plus dot 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 plus 2 times k plus 1, 2 times k plus 1 is equal to 2 times k plus 1, which is equal to, see, k plus 1, and when I write k plus 1 here, I get inside the bracket k plus 2. K plus 1 into k plus 2 is true. See, this we have to prove now. We have to now prove it. What? That this is true. So what I will do, I'll take LHS. Okay, let me take LHS. See here, this is my LHS. So LHS is 2 plus 4 plus 6 plus 8 plus 10 plus dot 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 plus 2 times k plus 1. Okay, now tell me students, here I have the last term that you see is 2 into k plus 1. So what would be the term just before this term? Wouldn't it be 2 times k? It will definitely be 2k. See, 2k, then the next is 2k plus 1. So this is my left hand side. But what we have assumed, if we go by that, if we go by that, see, up to 2k, up to 2k, what is the value? The value is k into k plus 1. It is true. We have assumed it. We have assumed that P of k is true. And under that assumption, 2 plus 4 plus 6 plus 8 plus dot 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 2k is k into k plus 1. So for this here, I will write k into k plus 1. Okay, so let me write. So the next step, I get k into k plus 1 plus, here I have 2 times k plus 1. Okay, now taking k plus 1 common. So if you take k plus 1 common, you will get k plus 1 out, you will get inside the bracket k plus 2, and you will be surprised that, see, you had started with LHS, you started with the LHS here, and see what are you ending up with? You end up with RHS. RHS. So here what you prove? You just now proved that if P of n is true for n equals to k, then it is true for n equals to k plus 1. Don't forget, you could prove it is true for k plus 1, it is true for n equals to k plus 1 only under the assumption that you had made it is true for n equals to k. Okay, see, you had made an assumption that P of n is true for n equals to k, which was 1, and just because you had made this assumption, you could prove that P of n is true for n equals to k plus 1. Okay, so I will now write here, therefore from step 1 and step 2 by principle of mathematical induction, by principle of mathematical induction, we can say that given proposition is true for all n natural. Come on, copy this. Start copying from here. So now we go for the second question. To prove by method of induction for all n natural, this proposition would be true. What is that? Look at the proposition left hand side. You are adding 3, 7, 11 and so on to n terms. And they're saying that if this way a series you have up to n terms, then the sum of all the n terms of the series will be equal to n into 2n plus 1. It will be equal to n into 2n plus 1. Now here one difficulty that we notice, that it is given 2n terms, but we are not given the nth term. In the proposition, the nth term is not given. Now because the nth term is not given, we will begin the we will begin the proof, but before that we will have to find out the nth term. So here I will find out nth term. See, on the left hand side, see here what I write. So, or I can say that my solution has already started. So I will write on LHS on left hand side, we have an AP. See, this is an arithmetic progression. How? 3, 7, 11. 3 plus 4, 7 plus 4. You see this? So it is an arithmetic progression. We have an arithmetic progression where the first term A is 3 and the common difference D is 4. Okay. Therefore, the nth term will be, as you know, it is A plus n minus 1 into D. So 3 plus n minus 1 multiplied by 4, that is 3 plus 4n minus 4, that is 4n minus 1. 4n minus 1 is the nth term. So what we have to prove? Okay, so the nth term here, the nth term will be 4n minus 1. So we have to prove that is therefore we have to prove that 3 plus 7 plus 11 plus so on plus 4n minus 1 equals to n into 2n plus 1. Okay, and this is P of n. This is P of n. Okay, this is my assumption. Okay, this is P of n, my assumption, the first step. Okay, now what? I go for step 1. What is step 1? I will prove that this P of n is true for n equals to 1. So step 1 I write, we will prove that P of n is true for n equals to 1. That is to prove that. Now see, when you say n as 1, you mean just one term. Now for one term, what will this P of n become? You can check. For one term, you will have P of 1. You will have P of 1. That is to prove that P of 1, which is just one term, that is here you will have 3. Got that? You put n as 1, so you'll be left with just one term. 4 into 1 is 4 minus 1, 3. So you have 3 equals to n is 1. So 1, 2 into 1 plus, so 1 into 2 into 1 plus 1. That is to prove that, P of 1, 3 equals to, P of 1 which is 3 equals to, see 2 plus 1 is 3, 3 into 1 is 3. That is to prove that this is true. That is to prove that 3 equals to 3. Now what we will prove? This is obviously true. So I will write which is obviously true. Now having proved that P of n is true for n equals to 1, now we will move for step 2. What is step 2? Step 2 is to prove that, or we will prove that, what we will do? We will prove that if, see in this, in step 2, we start with if P of n is true for n equals to k, then P of n is true for n equals to k plus 1. That is, in the second step, you need to follow that we have an assumption. See, we will make an assumption that P of n is true for n equals to k. And under this assumption, under the light of this assumption, we will prove that P of n is true for n equals to, we will prove that it is true for n equals to k plus 1. It is true for n equals to k plus 1. Okay. So you will first make an assumption. What assumption will you make? You will make assumption that P of n is true for n equals to k. So you write here, let P of n, which is P of n, which is this, which is 3 plus 7 plus 11 plus dot 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 plus 4n minus 1 plus 4n minus 1 equals to n into 2n plus 1 is true for n equals to k. See, this is my assumption. Let this be true. That is P of k equals to P of k, which is 3 plus 7 plus 11 plus dot 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 plus 4k minus 1. 4k minus 1 is equal to k into 2k plus 1. 2k plus 1 is true. Is true. So this is my equation number 1. Okay. This is my assumption. What is the assumption? The assumption is P of n is true for n equals to k. Now, using this assumption, I will prove that P of n is true for n equals to k plus 1. Okay, I will write here. Using the above assumption, we will prove that P of n is true for n equals to k plus 1. Okay, that is to prove that P of k plus 1. See, 3 plus 7 plus 11 plus dot 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 dot. See, when n is k plus 1, what you will have? You will have plus 4 times k plus 1 minus 1. This will be the nth term when n is k plus 1. So when n is k plus 1, just before that, what will be the term? The term will be when n is k. And what will that be? See, you put n as k plus 1, so you will get this. Just before that, what will be the term? The term will be n equals to k. So that is 4k minus 1. Okay? Equals to, you have to write n as k plus 1. K plus 1 inside the bracket 2 times k plus 1 plus 1. 2 times k plus 1 plus 1 is true. We have to prove this. Okay, that is to prove that P of k plus 1, which is 3 plus 7 plus 11 plus dot 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 plus 4k minus 1 plus 4 times k plus 1 minus 1 equals to k plus 1, and this is 2k plus 3. 2k plus 3 is true. So what I will do, I will start with LHS. See, I will start with LHS here. What is my LHS? See, my LHS is this. Okay. So I write here LHS, LHS. Now, but in LHS, you notice that in LHS, right from here to here, what is this equal to? It is equal to k into 2k plus 1. This we have already assumed. You see this? So here we'll have LHS is k into 2k plus 1 plus, multiply this 4 inside, 4k plus 4 minus 1. Okay. 4k plus 4 minus 1. So now you get here k, when you multiply, so you get 2k square plus k plus 4k plus 4k plus 3. That is 2k square plus 5k plus 3 plus 5k plus 3. That is equal to 2k square plus, I can write this as 5k, I can write here 2k plus 3k plus 3. So I take 2k common. So LHS, I take 2k common. So this will become k plus 1. And when I take 3 common, from the last two terms, I take 3 common. Here I took 2k common. So here I take 3 common. So I'll get 3 common, so k plus 1. Now we have two brackets, k plus 1 and 2k plus 3. You can check. This is your RHS. You check this, k plus 1 into 2k plus 3. So you will write which is RHS. Okay. Hence, we have proved that. Hence we have proved that if P of n is true for n equals to k, then P of n is true for n equals to k plus 1. Okay. So, therefore, by principle of mathematical induction, we can say that 3 plus 7 plus 11 plus so on plus 4n minus 1 is equal to n into 2n plus 1. What is it equal to? It is equal to n into 2n plus 1. I hope you followed it. So question number 4, we have to prove this proposition, wherein we have the left hand side is 1 square plus 3 square plus 5 square plus dot 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 2n minus 1 square, and on the right hand side we have n by 3 2n minus 1 into 2n plus 1. So the first thing we will do is we will take this as proposition P of n. So P of n is 1 square plus 3 square plus 5 square plus dot 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 plus 2n minus 1 square equals to n by 3 2n minus 1 2n plus 1. We are proving this by principle of mathematical induction. So what is the first step? Step one is we will write, see, step 1, we will prove that, okay, don't say we will find that, no, we will prove that P of n is true for n equals to 1. We will prove that this is true for n equals to 1. That is P of 1, which is, now see, when n is 1, you get the first term. And what is first term? 1 square. That is 1 square equals to, put n as 1, 1 by 3, 2 into 1 minus 1, that is 2 minus 1 and 2 plus 1. That is to prove that P of 1, which is 1 equals to, here you have 1 by 3, 1 into 3, which is 3. That is to prove that P of 1, which is 1 equal to 1, is true. What we have to prove? We have to prove that this is true. Okay, this is true. Okay, but what we understand, 1 equals to 1, okay, this is obviously true. 1 equals to 1 is obviously true, which is obviously true. Okay, so we have proved that the proposition is true for n equals to 1. See, students, when you write n equals to 1, it means in this, which is the nth term, you will put n as 1. So when you put n as 1, it is the first term. So remember, you will get just one term. And what that one term will be? That one term will be the first term. And the first term is 2 into 1, 2 minus 1, 1 square. Okay, so you proved that the left hand side is 1 and the right hand side is 1. So P of 1 is true. Then we go for the second step. Step 2. Now we will prove that if P of n is true for n equals to k, then P of n is true for n equals to k plus 1. That is we will assume that P of k, what is P of k? Tell me. P of k will be, just put n as k. In this proposition, put n as k. That's it. That is all. P of k, which is 1 square, 3 square, 5 square, 1 square plus 3 square plus 5 square plus dot 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 plus 2 into k minus 1 square, 2 into k minus 1 square equals to k by 3 into 2k minus 1 into 2k plus 1, which is true. This is true and this is number 1. We will prove that we have assumed that this is true. And remember, under this assumption, we will prove that P of n is true for n equals to k plus 1. This is true. I will write now. Using the above assumption, we will prove that P of k plus 1. What will be P of k plus 1? You can understand. It is 1 square plus 3 square plus 5 square plus dot 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 plus, you know, this in P of k plus 1, this term will definitely come. P of k plus, in P of k plus 1, n is k plus 1. So n k plus 1 will be the next term. So this term will definitely be there. So 2k minus 1 square plus 2 times k plus 1 minus 1 square equals to, put k plus 1, so k plus 1 by 3, k plus 1 by 3, and here you have 2k plus 1 minus 1, 2k plus 1 minus 1, and this is 2k plus 1 plus 1. Okay, is true. We will prove that this is true. See, this we have to prove. That is to prove that P of k plus 1, which is 1 square plus 3 square plus 5 square plus dot 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 plus 2k minus 1 square plus 2k plus 1 square. See, I multiply this 2 inside, so 2 minus 1 plus 1 square equals to k plus 3, k plus 1 by 3, and this is 2k plus 1, 2k plus 1 into 2k plus 3 is true. We have to prove this. So what you will do now, you will take this LHS, and remember, you will prove this LHS is equal to RHS. But remember that in this LHS, from here to here, okay, this is equal to this, which is already true as per our assumption. This is already true as per our assumption. Okay, so you may pause the video and go for this on your own and check whether you are getting the RHS when you start with the LHS. Go ahead. You will start with LHS and you will try getting the RHS. Just check whether you are getting it. Now we will start with, see, we will take the left hand side. So what do I have in the left hand side? The left hand side is, I have here, see, the left hand side I have is 1 square plus 3 square plus 5 square, 1 square plus 3 square plus 5 square plus dot 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 plus 2k minus 1 square, 2k minus 1 square plus 2k plus 1 square. Now see, this much is already assumed, this much is already assumed to be, it has been assumed by us to be equal to k by 3, 2k minus 1, 2k plus 1. So here I will write, which is equal to k by 3, 2k minus 1 into 2k plus 1. and here I have 2k plus 1 the whole square plus 2k plus 1 the whole square. Now I will take 2k plus 1 the whole square common. So 2k plus 1, not square, just 2k plus 1 common. I will get k by 3, 2k minus 1 plus 2k plus 1. I will take here now, simplify this. So 2k plus 1, and this will be, okay, so this will become 2k square, 2k square minus k, 2k square minus k plus 6k plus 3 upon 3. Okay, I'm taking the LCM. So now this 1 by 3 I write out, 1 by 3 is out, 2k plus 1, and inside the bracket I get 2k square plus 5k plus 3. Plus 5k plus 3. So as we already know that this is a quadratic. This is a quadratic. So the next step I will get here 1 by 3 2k plus 1, and this is 2k square plus 2k plus 3k plus 3. So it will become 1 by 3 and 2k plus 1, 2k plus 1. If I take 2k common, if I take 2k common, I will get here k plus 1. When I take 3 common, I get here k plus 1. So this gets me 1 by 3 2k plus 1, and this is k plus 1 into 2k plus 3. And you will notice that this is RHS. See, k plus 1 by 3, 2k plus 1, 2k plus 3. K plus 1 by 3, 2k plus 1, 2k plus 3. This is RHS. Therefore, you will write therefore, if P of n is true for n equals to k, n equals to k, then P of n is true for n equals to k plus 1. Therefore, by principle of mathematical induction, by principle of mathematical induction, the given proposition, is true for all n natural. Hence done. So in next lecture we will take few more problems. Enough for now. Thank you.
Thank you, sir. Bye, sir.